everyone. This is Miss Irene Lagan, your physics teacher for this week, and we will be talking about heat, work, and efficiency. To start with, let's know what is heat transfer. Let's consider two objects. Let this object be hot and let this second object be cold. The temperature of this hot object is 100 degrees Celsius, and the temperature of this cold object is 5 degrees Celsius. This hot object possesses more heat energy than this cold object. That is why the temperature of this hot object is high than the cold object. Now, the natural process of transferring heat energy or thermal energy occurs between these two objects. The heat energy of this hot object transfers to this cold object until both bodies reach the equal temperature. For example, when heat energy transfers from hot object to cold object, then the temperature of hot objects drops to 40 degrees Celsius, and the temperature of cold object rises to 40 degrees Celsius. This state is known as the thermal equilibrium. Remember this important point: if two objects are in thermal equilibrium, it doesn't mean that heat energy doesn't transfer between them. Rather than this, if two objects are in thermal equilibrium, still the thermal energy transfers between them, but the net flow of heat energy is zero. For instance, a 5 joules of heat energy flows from this object to this object. Then 5 joules of heat energy flows from this object to this object. Thus, the net flow of heat energy is zero. And these both objects are in thermal equilibrium. Therefore, remember that heat transfer is the flow of thermal energy between two objects, while temperature only measures the amount of thermal energy possessed by any object. Now let's go to the different methods of heat transfer. These are conduction, convection, and radiation, which will be discussed from the channel Mike Samartano. Let's watch this.
Let's talk about heat transfer. What we're really talking about here is how energy moves, specifically heat energy, and how it gets from point A to point B, whether it be here on the surface of the Earth, up in the atmosphere, or even out in space. Heat transfer occurs really in three ways, and these include conduction, convection, and radiation. Let's take a look at each of these, starting with conduction. This is heat transfer as a result of molecular contact. The best way to understand conduction is by thinking about an example. So here I have a metallic spoon, and I imagine holding a match underneath it. Now what we know is that that spoon is going to heat up, and not just the part of the spoon that's over the match, but rather the spoon as a whole. And the reason this happens is because of conduction. Energy from the flame is causing the molecules within the spoon to vibrate, and that's transferring energy from one to the next, to the next, to the next, until the entire spoon has warmed up. That heat has transferred throughout the entire material. Conduction is going to happen most effectively in solid materials. But let's not forget about convection and radiation. Let's look at convection. This is heat transfer through or as a result of density differences. Again, let's grab that match and let's think about this for a minute. I think we all know it's probably not the best idea to hold your hand above an open flame like this, and that's because a lot of the heat energy generated by that flame is going to rise. That is purely because of the process of convection. You see, what's happening is the flame is causing the air to expand. And when it expands, it becomes less dense than the surrounding air and therefore floats upwards. And with it goes some of that heat energy. That's what convection is all about. And this is going to occur most effectively within liquids and gases. Finally, let's think about radiation. Radiation is heat transfer by wave motion. Let's pull that flame up one more time. I think we know that because of convection, heat is going to rise, but it's also going to travel outwards in the form of waves of energy, electromagnetic waves. And that's the third type of heat transfer. Radiation is really interesting in that it doesn't need a material for it to travel. So this can occur out in open, empty space. In fact, this is how energy travels from Earth's sun to the surface of the Earth. And so if we look back, we have our three types of heat transfer: conduction, convection, and radiation. And it's important to know the key word that goes with each one. For convection, it's going to be density differences. For conduction, it's going to be contact. And for radiation, it's going to be waves.
We can sum up all three types of heat transfer in one diagram by looking at something as simple as the campfire. Imagine that you are camping and you hold a pot of water above that flame. Well, right now, in this one picture, we are seeing all three types of heat transfer taking place. There's conduction happening, as the flame is transferring energy directly to and throughout the pot as a result of molecular contact. Additionally, there's convection, as the heat from both the boiling pot and the flame itself is rising up as a result of density differences. And finally, there is radiation, occurring all around the campfire, as energy travels away from the flame in the form of electromagnetic waves. And that's a quick look at heat transfer. Energy is conserved. That is, the amount of energy before will always equal the amount of energy after. The first law states that when heat is added to a system, some of it remains in the system, increasing its internal energy, while the rest leaves the system as the system does work. Let's watch this example from the channel Conceptual Academy.
Let's look at a simple example to illustrate the point. A utility room with a heater pumps 500 kilojoules of heat into a living room. If the heater delivers 500 kilojoules of heat, the living room receives 500 kilojoules of heat, and no more or less than that. But suppose there's a toy car with a sail by the heating vent. The warm air flowing into the room pushes on the sail, which gets the car moving. A force is applied over a distance, which means work is being done on the car. Strictly speaking, the room won't be warmed by as much. Why? Because some of the 500 kilojoules of heat went to pushing the car. Let's make up some numbers here. Let's say 10 kilojoules of the energy went to pushing the toy car. That means the living room only received 490 kilojoules of heat, not the ideal 500 kilojoules. So heat added to the living room equals the heat received by the living room plus work done within the living room. Energy took different forms, yes, but remains conserved. Our accounting is good and none is missing. If we include heat and work in our discussions of energy conservation, then we're into an area of science known as thermodynamics. Thermo means heat. Dynamic means action. So with thermodynamics, we're talking about actions that involve the transfer of energy, heat. Our example of the toy car in the heated room focuses on what is known as the first law of thermodynamics, which is no more than energy conservation applied to thermal energy. When the accounting is proper, it all adds up.
As mentioned, the first law states that when heat is added to a system, Some of it remains in the system, increasing its internal energy, while the rest leaves the system as the system does work. Or in symbols, Q equals delta U plus W, where Q equals the amount of heat in joules, delta U equals internal energy in joules, and W equals work in joules. Remember, Q or heat is positive when added to the system. Q is negative when removed from the system. Work is positive if it's done by the system. Finally, work is negative if done on the system. Example: calculate the internal energy change for a process that absorbs 10 joules of heat while doing 15 joules of work on the surroundings. Again, we will use the GAPSA method. So the given here are, as mentioned, heat is being absorbed or added, so it is Q equals 10 joules, positive. Then we have 15 joules of work that is done on the surroundings. Notice what the problem is saying. It says that the work is being done on the surroundings, which means it must be done by the system. So that is why work is positive 15 joules. And remember, anything that is done by the system on the surroundings is positive. So we are going to calculate the change of internal energy, or the delta U. Again, the formula that we are going to use is Q equals delta U plus work, or we can get the delta U by transposing work, so the formula can be delta U equals Q minus W. Then substitute the given to the formula. So that will be equals 10 joules minus 15 joules. So the answer should be negative 5 joules. That is the final answer. For another example, go to sample problem 10.4, page 182 of your science textbook. There are three ways by which the second law may be stated. Let's make this law as simple as possible. The first statement is called Clausius statement. It simply states that heat flows naturally from hot objects to cold objects, never the reverse. Or simply remember from high to low. For any process, a natural flow will always be from higher energy value to lower energy value. For example, coffee. The temperature of coffee is higher than its cup, and as mentioned, from higher to lower. So the heat from coffee gets transferred to the cup, which is cooler, and that is why the cup gets hotter. Second statement is the Kelvin-Planck statement, which states that no heat engine can completely convert heat into work. Just remember that in this statement, perfect is impossible. That means for every real-world process, there will always be losses. That means you cannot convert all of your car's fuel into mechanical energy, which can rotate your car's wheels. Proof is the gases you see that is released by the engine. Or try bouncing a ball by throwing it up to the air. Observe that the level of bounce decreases with time because of the loss of energy which is transferred to the ground. Lastly is the entropy statement, which states that when a reversible process occurs, the entropy of the universe does not change. And when an irreversible process occurs, the entropy of the universe increases. When we say entropy, it is the thermodynamic measure of disorder. Let's now proceed to the third law of thermodynamics. Let's watch the video from the channel Teach Me to Science.
third law of thermodynamics. Let's start by defining the third law. The third law of thermodynamics states that a perfect crystal has zero entropy at absolute 0 Kelvin. A perfect crystal is defined as a substance that is perfectly ordered. At 0 Kelvin, there would be no vibrations within its bonds. So what does this mean? At 0 Kelvin, the atoms are not moving at all. In this case, there is only one microstate or orientation that this perfect crystal is allowed to have. At 0 Kelvin, there's no energy being input to change the microstate. Though this law holds true at extremely low temperatures, we are unable to reach 0 Kelvin.
According to the zeroth law, if the temperature of the two systems is equal to the temperature of the third system, then they are equal in temperature with each other. This can be understood using this example. Two glasses of water. Glass A contains hot water while glass B contains cold water. If we leave these two glasses on the table for some time, during this time, the temperature of the hot water falls the same with the room temperature. Hence, a thermal equilibrium is formed between the glass and the room. During the same time, the temperature of the cold water rises until it equals the room temperature, thus forming another thermal equilibrium. Till now, we know that the temperature of glass A is equal to the room temperature. We also know that the water in glass B is equal to the room temperature too. Hence, the temperature of water in both glasses are equal as well. This law can also be stated in terms of thermal equilibrium. When a system A is in thermal equilibrium with system B and system C, then the systems B and C are in thermal equilibrium with each other. The zeroth law is extremely important for thermodynamics as it draws light on the concept of temperature and thermal equilibrium. What is heat engine? Heat engine is a device that converts heat energy to mechanical energy. Now all heat engines follow a pattern of operation. Let's consider a hot reservoir and a cold reservoir. Hot reservoir has a temperature T1 or T hot, and the cold reservoir T2 or T cold. And we know that temperature T1 is greater than temperature T2. Thus, heat transfer will occur between this hot reservoir and cold reservoir due to temperature difference. If I ask you why heat transfer from hot reservoir to cold reservoir, what do you think is the answer? As mentioned before, it is a natural process or spontaneous process. Now, what will happen if I remove the cold reservoir? Will heat transfer occur? No, of course, because heat transfer only occurs when there is hot reservoir and cold reservoir, or if there is temperature difference. Remember, heat transfer will only occur when there is hot and cold reservoir. Hot reservoir is also known as the source, and cold reservoir is also known as the sink. Now let's consider that hot reservoir or source loses heat Q1 or Q hot. We then construct an engine between this hot reservoir and cold reservoir. Now this heat Q1 enters to the engine. The engine will convert a part of this heat Q1 into useful work, and engine will reject or expel a part of heat Q1 to the sink or cold reservoir. Let me simplify it further. When engine absorbs heat Q1 from the hot reservoir, it divides, meaning the engine divides the heat into two parts. The engine converts one part of Q1 to useful work, and engine then expels a part of heat Q1 into the sink as heat Q2 or Q cold. Thus, We can write heat Q1 absorbed by the engine from the source as Q1 equals Q2 plus W. Now, rearranging this equation, we get work equals Q1 or Q hot minus Q2 or Q cold. Efficiency actually tells us how much of the input heat is converted to work. Thermal efficiency of a heat engine is defined as the ratio of the output work to the input energy, or in symbols, it is equal to work divided by heat input or Q hat times 100, since it is often stated as a percentage. And previously, we mentioned that work is equal to Q hat minus Q cold. So, thermal efficiency equals heat input or Q hat minus heat output divided by heat input times 100. Sample problem: an internal combustion engine having a thermal efficiency of 25% produces 2,500 joules of work. How much is the input heat and how much heat does the engine reject? Let's solve first the first question. And again, we will use the GAPSA method. So the given here are thermal efficiency, which is 25%, and the work output, which is 2,500 joules. We are asked of how much is the input heat, or in other words, we are looking for the Q hat. The formula that we're going to use is thermal efficiency equals work divided by Q hat times 100. Then just substitute the given to the formula. So that will be 25% equals 2,500 joules divided by Q hat times 100. Rearrange the equation and the final answer will be Q hat equals 1.0 times 10 exponent 4 joules, or simply 10,000 joules. That is the input heat. Let's go to the second question. The given are still the same, plus the Q hat which was solved earlier. Then we are asked to solve for how much heat does the engine reject, or simply to solve for the Q cold, which is the heat that is rejected going to the cold reservoir. So we will use this formula. Work equals Q hot minus Q cold. Rearrange the formula, that will become Q cold equals Q hot minus work. Substitute, and the answer should be 7,500 joules. That is the heat that is being rejected. Ideal heat engine or Carnot engine was proposed by a French engineer named Sadi Carnot. And to find the ideal efficiency of this engine, we will use this equation. Ideal efficiency equals T hot minus T cold divided by T hot times 100. Remember, temperatures must be in Kelvin, and also take note that the greater the difference between the two temperatures, the greater the efficiency of the heat engine. Lastly, to attain the 100% efficiency, the temperature of the cold reservoir or T cold must be in 0 Kelvin or absolute zero. However, as stated in the third law of thermodynamics, this temperature can never be attained. Thus, no heat engine is 100% efficient. Sample problem: there are two Carnot engines A and B, operating in two different temperature regions. For engine A, the temperatures of the two reservoirs are 150 degrees Celsius and 100 degrees Celsius. For engine B, the temperatures of the reservoir are 350 degrees Celsius and 300 degrees Celsius. Which engine has lesser efficiency? So let's solve first the efficiency of engine A. So the given here are T hat which is equal to 150 degrees Celsius. Convert that one into Kelvin since we're going to use a Kelvin unit, so that will be 423 Kelvin. And T cold, which is equal to 373 Kelvin. The formula that we're going to use will be T hat minus T cold divided by T hat times 100. Substitute the given to the formula, so that will be 423 Kelvin minus 373 Kelvin divided by 423 Kelvin times 100. Try to solve it in your own. The final answer should be 11.8%. That is the efficiency of engine A. Let's now solve the efficiency of engine B. The given here are T hat equals 350 degrees Celsius or 623 Kelvin. T cold, which is 573 Kelvin. Same formula, which is T hat minus T cold divided by T hat times 100. Substitute the given to the formula, so that will be 623 Kelvin minus 573 Kelvin divided by 623 Kelvin times 100. Final answer should be 8.03%. So that means the engine that has lesser efficiency is engine B. Even though the differences between the temperature of hot and cold reservoir in both engines is same, the efficiency is not the same. The efficiency depends on the ratio of the two temperature and not on the difference in the temperature. The engine which operates in lower temperatures has highest efficiency.